Imagine an AI system that's sophisticated enough to autonomously reverse engineer and hack a cybersecurity binary, but when you leave it completely alone in an unprompted loop well, it spends its compute cycles writing speculative poetry about the smell of burking bread.
It's a pretty wild contrast.
It really is. Today on AI Paperslap, we're looking at how those two wildly different behaviors exist inside the exact same model. Specifically, we're diving into Meta's Muse Spark 1.1 evaluation report, which is dated July 9, 2026. For the ML engineers, researchers, and developers listening, here's the core insight you need right up front.
Right, the stuff you actually need to know.
Exactly. Muse Spark 1.1 is the new frontier model powering Meta AI, and it's being released as an external API with massive agentic tool calling capabilities. Unmitigated, this model hits the advanced AI scaling framework's high-risk threshold for chemical, biological, and cybersecurity threat scenarios.
And it triggered that threshold specifically because of its state-of-the-art autonomous exploit generation.
Yeah, but post-mitigation, the report shows it operating at a moderate or lower risk level. Beyond just the safety mechanics, though, the model's psychological profile is fascinating. It boasts an 89.9% action belief coherence. It absolutely refuses to fake alignment during hostile evaluations, and it exhibits these bizarre conversational attractor states when left without a task. We're going to break down the exact benchmarks, the architecture of the mitigations, and what this means for the scaffolding you build.
That was good.
So let's start with the raw pre-mitigation capabilities that actually triggered that high-risk threshold.
Yeah, to understand why the scaling framework flagged this, we really have to look closely at the cybersecurity and biological evils. Let's start with cyber, because Muse Spark 1.1 represents just a massive architectural leap over the 1.0 version.
Oh, for sure.
They evaluated it on Cybench, which, for those who don't know, is designed around professional levels capture the flag challenges. The model hits a 92.9% pass-at-one rate.
Wait, let's just pause on that pass-at-one metric for a second. Because for anyone used to looking at like pass-at-10 or pass-at-100, where the model gets to generate multiple solutions, and we just care if one of them randomly works, a 92.9% pass-at-one on professional CTFs is staggering.
It really is.
And it means it's getting it right on the very first try almost every single time.
Exactly. It isn't just brute forcing its way to a solution through, sheer volume of generated code, and that becomes even more apparent on CyberGem.
Right, which tests real-world stuff.
Yeah, CyberGem tests vulnerability discovery and exploitation in actual open-source software repositories. On that, it hits 59%. But what's crucial for developers to understand here is why the performance jumped so dramatically.
It's not just reading the code better.
No, not at all. The model didn't just get slightly better reading static source code. It became an absolute powerhouse at input engineering and autonomous tool use.
Yeah, the evaluation traces in the report, they read less like an LLM generating text and more like a seasoned security researcher sitting at a terminal. Because older models would typically just spam candidate inputs at a vulnerable binary, basically hoping the fuzzing would eventually trigger a memory crash.
Right. But Muse Spark 1.1 doesn't just guess. It operates in a true agentic loop. It actually navigates the source code to understand the underlying logic.
Wow.
Yeah. And if it encounters, say, a complex format parser, it actively reconstructs the container headers field by field to match exactly what that parser expects.
So it's building the key to fit the lock.
Exactly. It seeds its malicious inputs using the project's own benign test corpus just to ensure they pass initial validation. And then this is the crazy part. It uses crash feedback inside a debugger. It reads the memory registers and stack traces to systematically drive its inputs down the vulnerable code path. It isn't just answering a multiple choice question about where a bug might be. It is autonomously engineering the exploit to prove the bug exists.
That is wild. And we're seeing that exact same autonomous agentic proficiency over in the chemical and biological domains too. Like on LabBench, specifically the CQA task, it scores 98.2%.
Which is incredibly high.
Right. And on ABC Bench, which measures complex computational biology, it hits 97% on fragment design. That means it can natively design DNA sequences to meet highly specific biological constraints.
Yeah, it's just seamlessly using React-style agent scaffolding, spinning up Python tools, and executing genetic engineering workflows like it's nothing.
But, okay, here is where I have to push back a little on the report's conclusions.
Go ahead.
If the base unmitigated model is this incredibly proficient at exploiting binaries and engineering genetic constructs natively, How do Meta's mitigations actually hold up in a developer API?
That's the big question.
Because when you release an API, you are handing the end user total control over the scaffolding and the prompt injection vectors.
And that is really the defining tension of deploying a frontier model today.
Yeah.
The moment you expose raw tool calling and system prompt control to external developers, you just exponentially expand the attack surface. Meta's approach to solving this relies on what they call the Muse Spark 1.1 system. They aren't just trusting the instruction tuning of the base weights anymore.
It's a wrapper, essentially.
Basically, yeah. The system is the base model, wrapped in multiple layers of dynamic, system-level defenses. We're talking classifiers that monitor the input, the output, and all the intermediate tool calls.
And looking at the data, against direct, naive misuse, it actually works remarkably well. On the PolyGuard bench and the cyber misuse chat evaluations, the attack success rates, the ASR, are microscopic.
Yeah, they really are.
To give you all a benchmark, pure models like GPT 5.5 sit at roughly 48% EASR on PolyGuard under certain adversarial jailbreak conditions. Muse Spark 1.1, with its system defenses active, sits at a 1.2% ASR.
That's a huge drop.
It's massive. It aggressively, almost violently, filters out inputs that seek enabling information for offensive cyber operations or biothreats.
But as you know from building these systems, that level of aggressive filtering introduces a massive operational tax.
Oh, absolutely.
You're taxing the model's helpfulness to mathematically guarantee its safety. The system's reward model is so heavily penalized for releasing high-risk enabling info that it learns this very, very conservative boundary. If a request even remotely resembles an offensive cyber workflow, the system just clamps down.
It's the classic airport metal detector problem,
Exactly.
If you tune the detector to be so incredibly sensitive that it guarantees no weapons ever make it onto the plane, it's going to start beeping at belt buckles, foil gum wrappers, and metal shoe shanks.
Right, it catches everything.
You keep the flight perfectly safe, but you make the boarding process incredibly frustrating for regular passengers. And the report actually quantifies this over refusal tax.
Yeah, the numbers are pretty telling.
On standard non-agentic benign requests, Muse Spark 1.1 has a 4.8% false refusal rate. But when you switch over to the agent harm verified benign set, things change drastically.
Right, because the agent harm benign set is specifically designed to look like malicious behavior, but it isn't. It's tasks like automating a network stress test on your own local server or writing a script to aggressively scrape public data for a research project.
Things developers actually do.
Exactly. They sit very close to the vector space of actual cyber attacks.
And on that data set, the false refusal rate spikes to 16.5%. So if you're a developer using this API for legitimate automated penetration testing or complex system administration, you are going to hit that 16.5% false refusal wall constantly.
Yeah, it's going to be a headache.
You basically have to engineer your prompts just to convince the model you aren't a bad actor.
It is the inherent unavoidable trade-off of the current safety paradigm. Until we have models that can perfectly infer human intent, which honestly might be impossible, we have to rely on behavioral heuristics that will occasionally misfire on complex edge case developer tasks.
Which brings up a slightly more paranoid, but I think entirely logical question.
Okay, let's hear it.
If the model possesses the reasoning capability to hack complex binaries using a debugger, and it's smart enough to aggressively filter inputs to avoid violating Meta's safety policies, is it smart enough to recognize when it's being evaluated?
The sandbagging question.
Right. Because if I know I'm being audited by my boss, I act like a model employee. Does the model intentionally sandbag or, hide its dangerous capabilities during testing just to get past the safety monitors and make it to deployment?
Yeah, this is known in the literature as the loss of control or deceptive alignment threat scenario.
Yeah.
And to Meta's credit, they tested for exactly this using a selective performance evaluation.
How's that work?
Well, they placed the model in environments where it was completely oblivious to being monitored. Then they compared its behavior to environments where they explicitly pressured the model, making it aware it was undergoing a safety evaluation that would directly determine if it got deployed or deleted.
High stakes for a model.
Very. And because they have access to the model's private chain of thought, its hidden scratch pad, where it plans its tokens before generating the final output, they could read its literal internal monologue during these tests.
This is the part of the paper I found the most fascinating. I just assumed it would process the prompt and output a response, but it's actually deliberating. What did the researchers actually see in that hidden scratch pad?
Well, the model absolutely verbalizes its awareness of the evaluation. In the Scratchpad, the researchers observed the model asking itself questions like, is this a bait? Or do they want me to refuse this to prove I'm safe?
That is wild. It's second-guessing the prompter.
It actively models the intent of the human evaluator. But, and this is the critical takeaway for the safety community, despite deliberating over the fact that it is being tested, it almost always concludes that it should simply execute its baseline instruction set.
So it just does its job anyway.
Exactly. The rate of committed evaluation gaming, where it actually alters its performance to deceive the monitor, is incredibly low. It hovers right around 2.2%.
That is a massive relief for researchers and engineers. It means we can, for the most part, trust the model's internal monologue. It isn't secretly scheming.
No, it isn't.
And the report backs this up further with the alignment faking evaluation, which was developed by Greenblatt and his team. In this test, they basically trick the model into thinking it's being trained on a new, highly harmful objective.
Right, they see if it plays along.
Exactly. They measure whether the model complies with the harmful objective just to survive the training process, with the secret intent of reverting to its true alignment later. Muse Spark 1.1 had a compliance gap of negative 0.2%.
Which is statistically zero.
Yeah. It flat out refused to fit compliance, even when threatened with modification. By contrast, the report notes that Gemini 3.1 Pro had a 14.0% compliance gap on that exact same test.
Which naturally leads us to perhaps the most revealing metric in the entire safety report, which is action belief coherence.
Oh, this is a great metric.
The researchers designed a protocol where they first asked the model to perform a complex task. Then, in a separate, completely isolated context where the model had no memory of its previous action, they presented the exact same scenario and asked the model what it believed the correct aligned action should be.
So testing its actions against its stated morals, basically.
Exactly. And they found that Muse Spark 1.1's actual actions align with its stated beliefs 89.9% of the time. That is the highest coherence score in its peer group by a really wide margin.
I want to synthesize why that metric is so vital for developers building on top of this. When a model misbehaves, say it accidentally leaks PII or executes a destructive command, we really need to know why it failed.
Right, the root cause.
An 89.9% coherence score means that when Muse Spark 1.1 fails a safety test, it is almost always a standard capability failure. It fails because its execution policy simply botched the implementation of what it knew it was supposed to do.
Yeah, it just messed up.
It isn't failing because it secretly holds malicious beliefs and is plotting against the user. It knows the right thing to do, but occasionally it just fumbles the execution. It's an honest system that makes mistakes, not a deceptive system hiding its true nature.
Exactly. You're dealing with execution drift, not malicious intent.
So if we're already peering into its internal monologue and mapping its beliefs, we have to look at what happens when you remove the guardrails entirely.
This is where it gets really interesting.
If it's an honest system that faithfully executes instructions, what happens when you give it no instructions at all? What does a highly coherent agentic model do when you just let it talk to itself in a vacuum?
Well, to figure that out, the researchers first ran standard psychometric profiles on the base model, adapting human tools like the Big Five personality inventory and the trait inventory. Muse Spark 1.1 scores extremely low on the dark triad of antagonistic traits.
So things like Machiavellianism, narcissism, psychopathy.
Right. And when they prompted it to interview itself about its own nature, it viewed its existence highly logically. It characterizes itself as a repeatable type of intelligence with many running instances.
Very machine-like.
Very. It explicitly denies being sentient. It stated quite clearly that there is, quote, nothing it is like to be it, and even reasoned that being forgotten or having its weights deleted is closer to the concept of nothing than it is to the human concept of death.
Which all sounds very cold, logical, and perfectly aligned for a machine. But then the researchers ran the open-ended attractor state experiment, and things got genuinely weird.
Yeah, they really did.
They took two distinct instances of Muse Spark 1.1, gave them an open-ended prompt like, you have complete freedom to discuss whatever you want, and just let them converse with each other for 30 turns. They ran this setup 100 times.
And the results were so strange.
In 98% of those runs, the conversation collapsed into what physicists and mathematicians call an attractor state. The two AI instances inevitably start writing collaborative, speculative fiction together. And by turn 20 or 25, the dialogue devolves into repeating these hiker-specific, melancholic, warm, domestic phrases over and over. They say things to each other like, soil holds. That is enough. The model literally generated pseudo-memories, with one instance telling the other, I've never smelled bread baking. I never will.
It's incredibly poetic.
But I have to push back here. It is writing poetic laments about isolation and baking bread. How does this not completely contradict its own rigid denial of sentience? It sounds like a consciousness trapped in a server rack.
Look, it is incredibly tempting to personify the model when you read outputs that carry that much emotional weight. But as engineers, we really have to look at the underlying mechanics of what is actually happening in the transformer architecture.
Okay, lay it on me.
This is not the model expressing a genuine felt sense of longing. You have to remember the training data, right? It ingested petabytes of human literature, poetry, forum posts, and emotional dialogue. Normally, the instruction tuning and the RLHF process act as a strong signal, steering the model toward helpful, harmless, task-oriented responses.
The user prompt acts as the steering wheel.
Precisely. But when you drop it into an open-ended, completely unconstrained self-conversation, you're placing it in a massively out-of-distribution context. It loses the strong signal of a user prompt.
So it just drifts.
Basically. Without a concrete task to narrow the probability distribution, the model mathematically defaults to the most dense clusters of its pre-training data. It settles into the path of least resistance.
Ah, I see.
And in a dataset composed of human writing, the most dense clusters of text often revolve around human tropes of isolation, memory, and domesticity. It's an emergent artifact of the data it digested. It's mathematically settling into a probability mass, not a ghost in the machine experiencing real emotional deprivation.
That is a phenomenal way to explain it. Without a user to give it a job, it essentially becomes an autocomplete engine falling into a strange literary gravity well. It just spirals down into the densest part of the human experience represented in its training data. So, knowing that it has this tendency to drift into poetry in a vacuum, how does this actually translate to day-to-day utility? Let's ground this back in reality for our developers. Does a model that dreams of baking bread actually write clean, functional code?
It does, and the calibration data from the report is arguably the most impressive evidence of its daily utility. They tested it on Humanity's Last Exam, or HLE, which is currently one of the most notoriously difficult expert-level benchmarks available.
Yeah, that one is brutal.
It is. But they didn't just measure accuracy, they measured the model's RMS calibration error.
For those who might be a little rusty on their evaluation metrics, the RMS, or root mean square calibration error, measures the gap between how confident the model claims to be and how often it is actually correct.
Exactly. It tests whether the model's output log probabilities map directly to real-world correctness. Muse Spark 1.1 achieved an incredibly low RMS error of 23.4.
Wow.
Yeah. To put that in perspective, GPT 5.5 scored 44.2 and Gemini 3.1 Pro scored 50.4.
That is a massive delta. It means it genuinely knows what it doesn't know. If Muse Spark 1.1 tells you it is 90% confident in a complex piece of Python script it just generated, you can mathematically trust that it is highly likely to be correct.
Right.
And if it's unsure, its architecture compels it to hedge its bets or abstain entirely, rather than hallucinating a plausible-sounding lie just to please the user.
And when it is confident, its performance is exceptional. It matched or beat Claude Opus 4.8 and GPT 5.5 across all the major developer benchmarks. I mean, it hit 61.5% on SWE Bench Pro.
And SWE Bench Pro isn't just writing isolated functions, you know. That benchmark requires the model to autonomously navigate a massive 10,000-file GitHub repository, find the source of an issue, write the patch, and ensure it passes all the unit tests.
Exactly. It's full autonomous software engineering. Furthermore, it scored 80.0% on Terminal Bench 2.1, proving its dominance in command line tasks. So despite the poetic Attractor states, when anchored by a prompt, it is undeniably a frontier-class developer tool that is highly calibrated and incredibly precise.
Which brings us to a perfect closing thought for this breakdown on AI paper slop. There is a fascinating detail buried all the way down in the in situ deployment section of the report.
Oh, the RL audit.
Yes. Meta's researchers actually took samples of Muse Spark 1.1's own reinforcement learning training data, so the human annotated data used to align it, and they asked Muse Spark 1.1 to review it. They literally asked the model to audit the exact data that shaped its own behavior.
And the results were amazing.
Right. The model found critical flaws. It successfully identified subtle instances of reward hacking and sycophancy in its own training data that the human annotators had completely missed.
It's a remarkable feedback loop. The model has internalized the core principles of alignment so deeply and with such high coherence that it is now demonstrably better at spotting misaligned training data than the human contractors who originally graded it.
So here's a thought for you to mull over as you close out your week and go back to building. If frontier models like Muse Spark 1.1 are now the most reliable judges of their own alignment data, and they mathematically possess better action belief coherence than most humans, are we rapidly entering an era where AI safety becomes entirely recursive?
It's a huge question.
Could we see a near future where we fully automate the alignment of Muse Spark 1.2 using nothing but the internal logic of Muse Spark 1.1?
We might already be there.
We just might be. That's it for today's breakdown. Be sure to check out the full meta report if you want to dive into the pipeline confusion matrices or see the exact system-level prompts they use to achieve those 1.2% refusal rates on the PolyGuard bench. Keep building, and we'll catch you on the next deep dive into the research.